Hello and welcome back to my channel. In this video, we will be looking at fluvial processes. A river is a body of water flowing through a channel from highlands, such as hills or mountains, to lower lands, such as along the coast. The channel of a river is made up of a bed and two sides. These two sides are called banks. The cross-sectional area of the channel is the width of the channel multiplied by the depth of the channel. Water enters the river channel by direct precipitation as well as runoff. Runoff, in turn, includes overland flow, which is where water flows over the surface, interflow or through flow, where water flows sideways through the unsaturated zone, or base flow, which is where the water flows sideways through the saturated zone. When this water reaches the channel, it becomes channel flow. Now, channel flow can take three main forms. We have laminar flow, turbulent flow, and helicoidal flow. Laminar flow is a movement of water in a series of sheets. It is where the sediments are flowing in parallel lines. This is not a common flow in rivers, however, and it is not helpful in disturbing the sediments on the riverbed. Turbulent flow is a chaotic flow and involves water moving in eddies and swirls. Turbulence is more common and provides the upward motion in the flow, which allows for the lifting of sediments from the channel bed. Helicoidal flow is a secondary flow and is mainly found in meandering streams. It is a corkscrew movement where water moves at the or near the surface from the inner bank to the outer bank of a meander, then goes down and returns to the inner bank near to the riverbed. Now, not only are we interested in the pattern of flow, we are also interested in the rate of flow. Thus, we can talk about the velocity of the river. The velocity of the river is the speed at which the water flows through the channel. The velocity of the river is in turn influenced by a number of factors. These include the gradient of the slope over which the river flows, the amount of friction caused by the rough edges within the river bed, and the shape of its channel expressed as hydraulic radius. When we talk about the discharge of a river, we are talking about the amount of water that is passing a particular point within the channel. Discharge can be calculated by multiplying the cross-sectional area by the velocity of the river. The wetted perimeter is the total length of the bed and banks in contact with the water. Now the channel shape is expressed as hydraulic radius, and the hydraulic radius is calculated by dividing the cross-sectional area by the wetted perimeter. So let's look at these diagrams. For stream A, the cross-sectional area is 5 multiplied by 8, which gives us 40 meters squared. We can then find the wetted perimeter by adding 5 plus 8 plus 5 again, which gives us 18 meters. So now that we have the wetted perimeter and we have the cross-sectional area, we can calculate the hydraulic radius. To get the hydraulic radius, we divide the cross-sectional area, which is 40, by 18, which is the wetted perimeter, and this gives us 2.22 meters. For channel B, the cross-sectional area is also 40, since we multiply 2 by 20. The wetted perimeter is 24, which is the sum of 2 plus 20 plus 2 again. Thus, the hydraulic radius for channel B can be obtained by dividing 40 by 24, which gives us 1.66 meters. So we can conclude that channel A or stream A has a greater hydraulic radius. This means that there is less water in its cross-sectional area, which is in contact with the bed and sides. It therefore means that channel A or stream A experiences less friction, and with less friction there will be a greater velocity. We can also say that stream A is a more efficient stream, and we will talk about efficiency later on. When we talk about roughness, we are talking about the amount of frictional resistance water experiences when passing over land and channel features. Channel roughness slows down the velocity of the water as friction results from the contact between the water and the irregularities in the channel bed and banks, as well as the boulders, trees, etc. Now, as rivers flow through their channels, they can carry out three main functions: transportation, erosion, and deposition. That is, as a river flows, it will dislodge materials and will transfer the materials from one point to another, and then it will drop the materials. The river's ability to move water and sediments is known as the channel efficiency and is also shown by the hydraulic radius. Now, the graph that you are seeing is called the hjulstrom curve. The hjulstrom curve is a graph used to determine whether a river will erode, transport, or deposit sediment. It shows the relationship between the size of the sediment and the velocity required to lift it, transport it, or deposit it. The line at the top of the hjulstrom curve is the critical erosion curve, which shows the minimum velocity required to lift a particle or initiate erosion of a certain sediment size. The line at the bottom is the mean fall or settling deposition curve and shows the maximum velocity at which a river can be flowing before a particle or sediment of a certain size is deposited. The zone in between the critical erosion curve and the settling velocity curve is the zone of transport. Now let's look at the critical erosion velocity curve. This curve shows that sands require the least velocities to be dislodged from the bed, while small sediments such as clays and silts and large sediments such as pebbles and boulders require higher velocities. Now, this is because clays and silts are more cohesive in nature, so they stick to each other and stick to the bed, and therefore are more difficult to be dislodged. Gravels and boulders experience more frictional resistance due to their size and weight. The middle zone tells us more about the transportation of the sediments after they have been lifted or dislodged by erosion. It takes much more energy to lift sediments and start their motion than to maintain them in transport. Therefore, the velocities for transport are lower than that for erosion. Now, notice that a big gap between the critical erosion curve and the deposition line implies that sediments will be transported further, while a small gap implies that a relative drop in velocity causes a sediment to be deposited, so they can only travel short distances. Thus, clays are able to travel long distances after their uplift. They are able to travel longer distance than sands and gravels. Boulders and pebbles can only travel for a very short distance because of their weight. Now, let us focus on the settling deposition curve, which shows the maximum velocity at which a river can be flowing before a particle of a certain size is deposited. Notice that clays, once lifted, can travel the complete distance to the sea and will not be deposited. So clays can go all the way out to the sea, and this is why clays are important when it comes on to the formation of deltas. The maximum velocity it takes for boulders to travel before being dropped is much higher than sands and gravel. So larger materials will be deposited before smaller materials as velocity is reduced. Now we want to look at the three functions of rivers in a little bit more details, and we're going to start with erosion. Rivers can erode in three main directions. So we can talk about headward erosion, lateral erosion, and vertical erosion. Headward erosion is a process by which rivers erode upstream. Headward erosion will therefore lengthen the river channel. Lateral erosion is a process by which the river erodes sideways, and therefore lateral erosion is able to widen the stream channel. Vertical erosion is a process by which the river erodes its beds, or it erodes down, the river erodes downwards, which deepens the channel. We generally find vertical erosion in the upper course of a river, while lateral erosion is mainly seen in the middle and lower courses of the river. Headward erosion is mainly seen at the source of the river channel, but it can also be viewed in the upper course where there are waterfalls. So besides talking about the direction in which the river erodes, we can also talk about the method by which rivers erode their channel, as well as the load that they are carrying. And speaking of the load, we can talk about attrition. Attrition is a process by which the load being carried collide together and break up. Abrasion, also called corrosion, is where the river throws the material being carried against the bed and banks, causing the bed and banks to break up. Hydraulic action is different from abrasion in that it is not the materials which are the agents of erosion, but the force of the water itself, which causes the bed and banks and also the load to be worn down. And one way in which hydraulic action may take place is where the water is forced into cracks, and as it is forced into the cracks, it causes the cracks to expand, and when the water moves away from the cracks, they contract, and so over time the expansion and contraction cause the cracks to break up, or the rocks to break up. Now, while attrition, abrasion, and hydraulic action are all physical processes, solution is a chemical process. Solution, also called corrosion, not to be confused with corrosion. Corrosion is another name for abrasion. Corrosion is another name for solution. So corrosion or solution is a chemical process, and it is where there is a chemical reaction between the water and the minerals in the rocks. And this causes the rocks to be worn down chemically. Now, we also can talk about methods of transportation. Let's first talk about solution, and let me make the point clear that while solution is a type of erosion, solution is also a type of transportation. So solution is where minerals are being transported by the water. So the minerals are dissolved in the water, and so they are carried naturally in the water. Then we have suspension, which is where clay and silt sediments are floating in the water. Saltation is where pebbles bounce along the river. This might also involve large sands bouncing along the riverbed. Traction involves boulder-sized sediments being rolled along the riverbed. So we have already talked about the hjulstrom curve, and we understand that the size of the materials matter when it comes on to erosion and transportation. All right, so when we look at clay-sized sediments, we said that even though they are difficult to be dislodged, once they are dislodged and they become a part of the water, they are so light that it's easy for the water to transport them over long distances. So they will float in the water. When it comes on to large sands and gravels or sometimes pebbles, what happens is that the water is able to lift them, but it cannot maintain them. So the water will lift them, then drop them, then lift them, then drop them. And so over time, what is happening is that the sediments are bouncing or hopping along the river bed, and it moves that way. With boulder-sized sediments, the river is unable to lift them because they are so large. But where there is a large enough discharge, or where the volume of the water is large enough, the force of the water can push these boulders, and therefore they will roll along the riverbed. Now, as we focus on transportation, it is also important that we make a distinction between competence and capacity. So the different methods that we just looked at in terms of transportation are mainly related to competence. Competence describes the maximum size or weight of materials that the river can transport. So when we talk about competence, we can look at sediments that are small versus sediments that are large. Capacity is the total amount of load that the river can carry at one time. So when we look at capacity, we can compare a small amount of materials being carried with a large amount of materials being carried. All right, so that is the main difference between competence and capacity. Now, both competence and capacity increase with discharge, and therefore competence and capacity will be greater during times of floods. And so on to deposition. When we talk about deposition, we don't really talk about methods of deposition. What we will focus on instead are the different ways that materials can be deposited. We learned from studying the hjulstrom curve that materials will largely be deposited when the velocity is not great enough to carry them. So what we will find is that larger sediments will be deposited before smaller sediments. And when materials are deposited in this way, then we can say that they are being deposited in a sorted manner. So the diagram that you are looking at is showing materials being deposited in a sorted manner, from boulders to cobbles to pebbles to sand to silt and finally to clays. Now, what are some of the ways that deposition can occur. Deposition will occur when there is low discharge following periods of precipitation. Let me repeat. Deposition will occur when there is a low discharge following periods of low precipitation. In other words, the volume of the water in the channel will be low and will be unable to transport the material, and therefore deposition will occur. Deposition will also occur when stream energy is insufficient to carry the entire load. This means that larger materials will be deposited before finer materials. Deposition occurs when there is less velocity, such as when the river enters the sea. It occurs when the water is shallow, such as on the inside bend of a meander. Deposition occurs where the channel is widened, which increases the friction and therefore slows down the river. It can occur as the river is passing over permeable rocks, which will cause some of the water to infiltrate into the ground and therefore reduce the volume of water in the channel. It can increase when there is a sudden increase of load, such as when there is a landslide. Deposition also occurs when the river overflows its banks and the materials are deposited outside of the channel. Okay, so thank you very much for watching. I really hope that you learned something. As usual, don't forget to like, to share, and to subscribe to my channel.